Hello again. Welcome to another review session for your final exam in Calculus 3208. Second session now of, I believe there's going to be 7 in this final unit. Wow, so we're getting close, down to the wire. Alrighty. We're looking today at something called the natural logarithm. So in the last session we looked at Euler's number, and as an exponential function we had this y equals base e to the power of x. Well, natural logarithm is kind of a natural consequence of that. So let's see where it takes us, shall we? Alrighty, so the natural logarithm is the logarithm with base e, and it's an inverse for what we saw last time, which was f of x equals e to the power of x. And we're going to talk about laws of logarithms, which we should already be fluent in, the laws of logarithms, and we'll talk about how they can also apply to the natural logarithm, or the natural log. And we're going to talk about differentiating the natural logarithm and then sort of see some of the implications of what its derivative are. All right, so those are the things we're going to highlight today, so let's get started. First off, we're going to talk about the same thing we saw last time, which was the exponential function y equals e to the power of x. So right here, f of x equals e to the power of x. And I've graphed it here in blue on this set of axes that you can see. And then to find out what its inverse should look like, we should all know you just reflect that over the line y equals x, and we'll get an idea of what the inverse function should look like. That's a better x. So if I reflect that blue line, or curve I should say, over the y equals x, we get f inverse, which is equal to the log of x. So this is how we write log base e, which will be the inverse of exponential base e. But instead of writing out all those letters all the time, mathematicians are a little bit lazy, so we abbreviate it as lnx. So lnx is actually what we call the natural log. So it's the natural logarithm. And I believe we actually refer to that as, most people just pronounce it as the ln, as in go cut your lawn, the grass is too long. So we call it the ln of x, okay? So we say log base e of x is just called ln of x. All right, so let's compare the two graphs that we have. Now, it shouldn't be anything really surprising here, since most of you, or should be maybe all of you by now, I would say, have studied exponential and logarithmic functions in another course. So let's take a look. So we'll look at the properties of the function f of x equals e to the power of x, and we'll compare them to its inverse, f inverse of x equals ln x. So let's put all that together then, shall we? First of all, let's look at the domain of each function. So for e to the power of x, we can see that it stretches as far as we want to the left, so all the way to negative infinity, and it's going to increase forever, but it does keep going out to the right forever as well. So it's going to go negative infinity to positive infinity. And for its range, it's bounded by the x-axis here. It's actually asymptotic to that, like all exponential functions are. And it increases upward forever, so its range will be 0 to positive infinity. And for the, oh, sorry, that's it down here. There's its range, 0 to positive infinity. Then we'll look at the natural log function. I'm reading sideways instead of up to down here, sorry. So we're going to go for the natural log function for its domain. We have to start at the y-axis, although not quite there, and then go all the way to positive infinity. So the domain of the natural log is 0 on to infinity. And its range, we can go downward for the y values as far as we like, so negative infinity. And it gets really, really slow as it increases, really slow forever, but it does go on forever. So its range actually goes negative infinity to positive infinity. We should remember, it's a really important consequence of this, and you know this from your other course as well, but that the domain of the exponential function should be the same as the range of the natural log, and vice versa, the range of the exponential should be the domain of the natural log, because they are inverses of one another. And that's what inverse means, partly. Okay, so let's talk about their asymptotes. The horizontal asymptote that we have right along here for y equals e to the power of x is on the x-axis. So it has a horizontal asymptote at y equals 0, whereas the logarithm function, the natural log, has its asymptote on the y-axis, which makes sense because if I reflect on a diagonal line, that's what I'm going to get. So I have a vertical asymptote at x equals 0 for the natural log. So let's look at intercepts. It should be fairly straightforward as well. For y equals e to the power of x, we have a y-intercept at 0, 1. And for y equals, or f inverse equals ln of x, we have an x-intercept at 1, 0. So that means we have no x-intercept for e to the power of x, and no y-intercept for the ln of x, okay? Because they're asymptotic to those axes. Cool. All right, let's roll right along here, shall we? we've got to look at now, all right, laws of logarithms. These are important, and I know that we know these already, but let's just put them in the context of the natural log. So now we're looking at the laws of logarithms in the context of the natural log, because they're going to be really important, especially in the next couple of sessions that we look at, some of the other things that we do in terms of derivatives and things with logarithms. So if we look at the product sum rule, remember that if I have a logarithm, and it doesn't matter what base, it works for base e like any other, a log of a product is the same as the sum of the separate logs. So basically, if I have two logarithms added together with the same base, I can write them as a single logarithm as a product of the arguments. Or if I have a logarithm whose argument is a product, I can separate that into the sum of two logarithms where each logarithm has its argument to be the factors of that original product. Wow, that's a lot of words. You can see it better than I can tell you. Same thing goes for quotient difference. The ln of a quotient is just the ln of each of those two parts of the quotient subtracted, so it's a difference. You can put them together or separate them whichever order you want. And we have a power or a multiple rule. So this is the one that sometimes folks get a little confused, but look carefully. The exponent has to apply only to the argument. So if I have a ln, or any logarithm for that matter, of an argument that has an exponent, the exponent then can be, sometimes I call this, my students will be able to tell you, the floater rule. So you can float that exponent out in front and make it a coefficient. Okay? So, or you could take a coefficient on a logarithm and float it up to be the exponent, but only of the argument, not of the entire expression. Wow. Okay. We're going to do something fun now? Let's hope. Let's see what's coming. Oh, this is the good stuff. All right, derivatives of logarithms, of natural log anyway. So we're going to start with the function y equals ln of x, and we're going to see if we can figure out what its derivative is. And this will remind you of, because it's basically the same method that we use to derive our actual derivatives, or that we use to differentiate the inverse trig functions. So this is a method that is really just the derivative of any inverse function, but we're going to apply that method in this case to find the derivative of ln. So here we go. So the first thing we do is we change the function from the original form into its sort of inverse form, which in this case goes from log form to exponential form. So we say e to the power of y equals x instead of y equals ln of x. So when I have that, then I'm going to differentiate. Okay, I do that because I know how to differentiate e to the power of stuff, and I don't know how to do this one yet. So I'm going to cheat and sort of sneak in the back door here. All right, so if I differentiate that now, it becomes an implicit function, so I have to use implicit differentiation. So notice that when I take the derivative of e to the power of y, it's just e to the power of y. But chain rule, because it's an implicit y as a function of x, becomes multiplied by dy over dx. So that's the trick. And the derivative of x, of course, is just 1 if we're differentiating with respect to x. So let's solve to get dy over dx all by itself. So then we have dy over dx equals 1 over e to the power of y when I just divide both sides by e to the power of y. And here's the problem. I started with a function y, that's a function of x. I'd like it if I could have its derivative as a function of x as well, instead of as a function of y itself. So what we do is we make a real quick substitution, and we replace the y in the exponent here with ln x, because we know that they're equal. That's what we started with. All right, so when we get that, then there's only one more step, and we should realize that e to the power of ln x is just x. Why? Because they're inverse functions of one another. And remember, an inverse function will undo its inverse. Any function and its inverse undo each other, like +2 and -2, square and square root, spaghetti and meatballs. No, wait, that's not quite the same thing. All right, but you get the idea. So the derivative here, dy over dx, is just 1 over x. Rock and roll. Let's see what's next. Okay, we're going to put some of these things into action now. So we've got to simplify some logarithmic expressions using our laws of logarithms. So in the first one here, I've got some addition and subtraction of logarithms. So I want to collapse all that together, but I can't do that if I have coefficients in front of the logs. Not allowed. So I remember that I can use my exponent rule here, or my power rule, or whatever the kids are calling it these days, and I can take all those coefficients and turn them into exponents on the arguments. Now, I almost wrote limit there. How about that? Too much calculus these days. This one here, this is already x to the power of a half. Raising that to the power of 3, I'm just going to quickly make that 3 over 2. I hope you're with me. I think you are. And then I'm going to subtract ln of x cubed. So for all of that, now what I need to do is anything that's got a positive in front of it, or a plus sign, is going to become part, when I make it a single logarithm, is going to become that argument. Speak clearly. That argument will become part of the numerator, so it's going to be x squared times x to the power of 3 over 2, because both of those are positive, and then divided by x cubed, because we have to divide when it's a difference. Okay, so now I have to combine all of those exponents together. So this is like a 4 over 2 and a 3 over 2, which would make 7 over 2 and 6 over 2. Uh-oh, that's just ln of x to the power of a half. And if you wanted to write it in a cooler looking way, that's ln of the square root of x. And you've got it. Okay, so for the next one, I've got a difference. So I'm going to have a quotient when I put these two logs together. But first thing is I got to float that exponent up on the argument. And it looks like this guy right here is going to factor. So I'm going to do those two things in one foul swoop here. So I'm going to make a single logarithm. And, not a limit, a logarithm. And for that log, I'm going to have my numerator will be this guy, but I'm going to write them in factored form. So it's going to be x minus 3 times x plus 1. And the other part will have to be x plus 1, but when I float that exponent up, it becomes squared. Okay? So a real quick simplification, x plus 1 and x plus 1 squared reduce there, and I just get the ln of x minus 3 over x plus 1. Now there are some non-permissible values happening there, but that's sort of an issue for your other course. We're not going to get into that right now because it doesn't directly affect what we're doing. So we're not going to worry about those things right yet. All right, so here in the next one, I've got, again, an exponent there that I have to deal with and an exponent there and a factoring issue. Before we put them together, that's a lot of stuff. Let's do those separately. So we'll say the natural log here of x minus 3 squared, subtract the natural log, and I'm going to factor this one now while I'm at it here. So this is x plus 5, product sum here, and x minus 3. And then I'm going to add the natural log of x cubed, which is what I have next there. Okay, so when I have all that taken care of, then I can combine my logarithms. So this becomes one single logarithm. So ln, anything with a positive in front, upstairs, anything with a negative, downstairs. So this is going to be x minus 3 squared, and x cubed is going upstairs too, but the other business has to go to the basement. So it's x plus 5 times x minus 3. And I can reduce this much of it anyway, cancel those out, and we just have the natural log of x minus 3 times x cubed all over x and 5. Okay, we got it. That's it. It's not rocket science. Rocket science is tomorrow. Just kidding. Next, we're going to take some derivatives. So this will be sort of the great pinnacle of our study of the natural logarithm here. So we have to differentiate. So let's take the derivative of each of these expressions that involves a natural log. Remembering that if y equals ln x, then y prime is 1 over x. So the first case, I have a quotient rule. The derivative of ln, which is the numerator, is 1 over x, multiplied by the denominator, which is sine x. Then I have to subtract the derivative of sine x, so that's cosine x, times the numerator, which is ln x. And all that is divided by sine of x. I have to square it, so sine squared x. So that's just pretty straightforward quotient rule there. Can we simplify that? Sure, what the heck, let's do it. So if I simplify that, we're going to have to multiply this stuff over here by an x to get that common denominator. So it's sine of x minus x cosine x ln x, all divided by x times sine squared. So I did that rather quickly, but that's the simplification thereof. Okay, so I'm just going to take that and move it out of the way for a sec so we can have some space for the other one. I'm not going to delete it entirely, not yet anyway. Well, maybe I am because I got it all screwed up there now. Let's delete it. Okay, bye-bye. So let's look at the next one. We've got ln of cosine squared of x. So this is going to require some chain rule here, and everything's all nested together. So outside function first is ln, so it's 1 over the argument, which is cosine squared. Then I multiply by the derivative of cosine squared, which is 2 cosine x, multiplied by the derivative of cosine, which is negative sine x. So can I simplify? Sure I can. One of those cosines and that cosine are down to the glue factory, and I end up with -2, and then I've got sine x over cosine x, which I believe might be -2 tan x. That's a nice way to write that one. Look how concise that is. It's very pretty. Okay. Now, f of x equals x ln x minus x. Ooh, I like this one. See how many of you remember this, and some time from now when you study integral calculus as well, because it's going to be one that will come back to haunt you a little bit later on. Okay, so x ln x minus x. Let's differentiate. First things first, I've got a product here, and then just a single term by itself. So for the product, the derivative of x is 1 times the natural log of x, plus the derivative of ln is 1 over x times x, and then I subtract the derivative of x, which is 1. So when I put all this together now, I've got ln x plus 1 over x times x is 1, and then subtract 1, and these two guys can get eaten, and we just have ln of x. Aha, so ln of x is the derivative of that. Guess what that means? And this is just a little tip for you for later on, eh? Then the antiderivative of ln looks like this. Not easy to come up with. All right, let's try the last one. F of x equals that business. So f prime of x then is going to be equal to the derivative, oh, lots of layers here, 3 of them. The outermost layer is a cotan. So the derivative of cotan is negative cosecant squared of the argument, which is ln of x squared minus 3. Okay. Then I multiply by the derivative from the next layer in, which is that natural logarithm. So it's going to be 1 over its argument, which is x squared minus 2. And then I multiply by the derivative of what's inside the ln. And what's inside the ln there is x squared minus 2, so its derivative is 2x. Wow, okay, so we get all that to fit together somehow. Then we're going to try to simplify this. There's not really a whole lot we can do except maybe write it in a neater form. So all upstairs I'm going to have -2x times cosecant squared of the natural log of x squared minus 3, all divided by x squared minus 2. That's about as nice as I can make that one. Okay, nice differentiation, folks. Hope you like that. I did. Okay. Here's the your turn question. Some derivatives for you to compute. Have fun. They're a little bit more complicated than the ones we just did. We're climbing the ladder here. We're going for the gold. Hopefully you're going to work it out. Thought you needed a little bit of a challenge today. So I'm going to jump to the solutions for that. So there's the solutions. Lots of fun stuff with logarithms. Okay, I hope you're getting those right. And if you're not, you're figuring out why. And let's take a look now at the key ideas summary. The natural logarithm is, as we said, ln x is log base e. Remember that, where e is just Euler's number. And it's important to note that f of x equals e to the power of x, and its inverse, ln x, they're inverses of each other. The same laws of logarithms apply to ln x in the same way they do to logarithms of other bases, so don't forget that. And using the method of differentiating an inverse function, it can be shown that the derivative of ln is 1 over x. And as always, it's important to practice differentiating functions when they involve combinations with ln by using the product, quotient, and chain rules with all kinds of other functions. Wow, that was fun stuff. I really enjoyed this one. Hope your studying's going well. If you got any questions, post them up. I'll do my best to try and answer them for you. Thank you very much.